Aloha, I hope you're well. This lecture, we're going to continue our discussion of different types of bonds leading up to a discussion of biologically important macromolecules. Exam-like questions, so let's give a shot at explaining half-lives. If carbon-14 has a half-life of 5,000 years, what does that mean? A half-life of 5,000 years means that for a given volume or a given number of carbon-14 atoms, half of them will degrade to carbon-12 in that amount of time. So if you expect to find 120 units of carbon-14 in a live tree branch and you find 30 in your sample of charred wood from an old fire pit, how old is the wood from the fire pit? Well, it's a question of how many half-lives. So one half-life, 5,000 years, 120 units of carbon-14 would degrade to 60 units of carbon-14. And so another half-life would be from 60 to 30. So that would be two half-lives. So 5,000 plus 5,000, so your estimate is 10,000 years old. Why is the atomic mass of carbon 12.01? Well, that's because it's an average of masses for all the carbons, carbon-12 and carbon-14, corrected for their relative abundance. So there's a lot more carbon-12 than there is carbon-14. That's why it's an average of 12.01. So we talked about the likelihood that atoms are going to get involved in bonds, and that's based on the completeness of their outermost shell. And we started discussing different types of bonds. We started off looking at covalent bonds where electrons are shared between atoms. We saw that there are two types of covalent bonds, the non-polar covalent bond where the electronegativities of the atoms involved in the bond are the same or relatively close, so that the result is that the electrons being shared are shared equally between the two atoms. So there isn't a relative charge difference between the ends of this molecule. When the atoms involved have different electronegativities, the atom with the stronger electronegativity will have a tendency to draw the electrons toward it more often. So because the electrons are spending more time around that atom becomes a little bit negative compared to the other one. And so there's a charge polarity across the molecule, a relative positive charge, in this case around the hydrogen, and a relative negative charge. You can see the density of electrons much denser around the oxygen in the bottom right-hand corner of this slide. And you can see a general rule of increasing electronegativities as you travel from the lower left-hand side of this periodic table of elements to the upper right-hand side, just shy of the row of noble gases, of course. When you have a polar covalent bond, this leads to the possibility of hydrogen bonds, where the small negative charge of the oxygen in a water molecule is attracted to the small positive charge of the hydrogen of a different water molecule. And those hydrogen bonds between water molecules give water its cohesive nature, among other things. Hydrogen bonds don't exist just in water. I give you examples of hydrogen bonds in cellulose, as well as hydrogen bonds that keep the nucleic acids of a DNA strand held together. So water is very polar. Being polar, that enables water to be a very, very good solvent. In other words, molecules that are hydrophilic can dissolve in water. Water is also highly cohesive. That enables water to climb the plumbing of plants, the vascular tissue of plants, because the water molecules stick to each other and are drawn up the vascular bundle. Water also expands when it freezes, and this is a very, very unusual property that enables life on this planet. It enables gigantic oceans to remain liquid. If water if water's densest state was the solid state, like most other things, all the oceans would freeze. But the way things are, ice floats and acts as a blanket over top of the water to enable the water below the ice to be warmer. So the three different states of water are described in this slide, showing that the most spacious state of water is the gaseous state, where there aren't hydrogen bonds between water molecules. Liquid state is a medium state, where many of the water molecules are bonded together with hydrogen bonds. The number of water molecules that are associated by hydrogen bonds depends very much on the temperature of the water. The hotter the temperature, the faster the water molecules are moving, and the fewer of them are joined by hydrogen bonds. The energy of movement, or kinetic energy, is sufficient in hot water to break hydrogen bonds. And once those hydrogen bonds are broken between individual water molecules, well, then the water can evaporate and go into the gaseous state. When water freezes, the lattice that's formed among individual water molecules once they stop moving enables them to be joined with an optimum number of other water molecules, and that creates the crystal state, which occupies more space than the liquid state. This explains how sweating works. Sweating works by transferring the energy, the heat energy of your body to the kinetic energy of the water that's been put on the outside of your skin. That kinetic energy breaks hydrogen bonds between individual water molecules and results in the water on the outside of your skin evaporating. And I give you a short aside on how ice skating works. The pressure of the blade melts the ice, and so you end up floating on water. Cohesiveness of water enables water striders to live on the surface of water. It also enables the water in the roots, being picked up by the roots of plants, to be transported to the top of a tree, because the water molecules are sticky with each other. The polarity of water enables hydrophilic molecules like glucose to become dissolved in water. And the way that works is that polar covalent bonds in the glucose molecule, and you can see the white balls and the red balls, those are hydrogen atoms and oxygen atoms. The polarity of those bonds enables a water molecule to have a hydrogen bond with an OH part of a glucose molecule, and the water molecule surrounding this glucose molecule cause the glucose to be dissolved in water. So hydrophilic molecules have some polar covalent bonds, whereas the hydrophobic molecules, and you see that on the right-hand side of the slide, hydrophobic molecules do not have that polarity and so are not able to interact with the polarity of water. An ionic bond happens when two atoms are in association with each other, and one of the atoms has such a strong electronegativity that it doesn't just have the electrons from the other atom spend more time around it. In fact, it just simply steals an electron from the other atom. So you see this with chlorine. Chlorine has very high electronegativity, around 3, and sodium has very low electronegativity, about 0.9. And so the high electronegativity of chlorine enables chlorine to steal an electron, emptying the outer electron shell of the sodium, filling the outer electron shell of the chlorine. That gives the chlorine a full negative charge and causes the sodium to have a full positive charge. The opposite charge attraction is what constitutes an ionic bond, as we see in sodium chloride or salt, table salt. So ionic bonds are electrical attractions between oppositely charged ions. So when you throw salt into water, what happens are the individual water molecules form what are called oriented solvent shells. The water molecules line up so that the partial positive charges of the hydrogen atoms of a water molecule are oriented towards the negative charge of a chlorine. And in other water molecules, the negative charge of the oxygen of a water molecule is oriented toward the positive charge of the sodium. And so these similarly oriented water molecules align themselves around the negatively charged chlorine and the positively charged sodium and cause salt to be dissolved in water. The next kind of bond, if you will, it's not really a bond, but it acts like a bond. This is called the hydrophobic effect, and this is where this is a phenomena where hydrophobic molecules become associated with each other when they are thrust into a hydrophilic environment like water. You can think of it as a molecular version of circling the wagons. What hydrophobic molecules do, the individual hydrophobic molecule is very unstable in an aqueous or watery environment because there's no way for the water molecules to interact with the nonpolar molecule, the hydrophobic molecule. So when you have a whole bunch of hydrophobic molecules all thrust into this aqueous environment, the hydrophobic molecules align next to each other, and by doing so they exclude contact with water, so that the more hydrophobic molecules are present in the water, the more of them will clump, and only the very periphery of the collection or the group of these hydrophobic molecules, only the periphery will be exposed to water. This clustering of the hydrophobic molecules and reducing their individual exposure to the water is called the hydrophobic effect or hydrophobic association, and enables the hydrophobic molecules to be collectively more stable in a watery or hydrophilic environment. So this is how soap works. The hydrophobic tails of soap can associate with grease. So the grease in your clothes or the grease on your dishes, and they form little balls of grease that are surrounded by detergent molecules inside the aqueous environment. So that's how grease or oil or dirt is lifted off of material or your plates in the cleaning process. The next kind of bond I want to talk about is the van der Waals interaction. The van der Waals interaction is responsible for how a gecko can walk up your wall and across your ceiling. This is a photograph of a gecko that I saw on the running board of the car next to me in the Ke'au Mall parking lot. That's the attraction between the toes of this gecko and the surface of the car. That attraction is called the van der Waals force. And the way that a van der Waals force works is that the toes of a gecko are actually covered in tiny, tiny microscopic hairs. And if you zoom in, as you see on the left-hand panel at the bottom of the slide, each of the little hairs on the toes of a gecko, the ends of them are all split up, all frayed up. And what that enables is for, at a molecular level, there to be very, very intimate contact between the split ends of the hairs on the toes of a gecko and the surface of the wall or the car or whatever it is that they're walking across. When there's this kind of intimate molecular interaction, the movement of electrons around individual atoms can become synchronized. And when they are synchronized, the electrons from individual atoms end up being on the same, let's say the left-hand side of an atom. When two atoms are side by side and both of them have their electrons on the left-hand side of individual atom, that means that the right-hand side of both of those atoms have a very slight positive charge because the electron's on the other side. So if two atoms are side by side, and the electrons for each of those atoms are both on the left side of each of those atoms, and the right side of both of those atoms are a little bit positive, then the little bit positive of the atom on the left-hand side, the little bit positive, its right-hand side is attracted to the little bit negative on the left-hand side of the right-hand atom. Yeah, that's mental gymnastics, but I think you can follow it. And have a look at the diagram. You can see that there's a slightly blue side of an atom being attracted to a slightly red side of the atom beside it. Those synchronized asymmetries in neighboring atoms are the attraction between those tiny and very, very transient. But because they're synchronized, the transient is complementary. So the atoms are attracted to each other. Now, it's a very, very weak bond. Because the electrons are moving at the same time in the same way, the bond remains secure, although very, very weak. The thing that enables the gecko to walk across the ceiling is there are a bazillion of these individual frayed ends of the hairs on the ends of the toes of the gecko walking across the ceiling. Of course, this has a very narrow window in which it will work. The hairs at the ends of the toes of the gecko need to be very, very close. If they pull apart, the bond is lost. Have a look at this video. I think it's a good video, and it shows how people are trying to scale up this effect. Spider-Man gloves. Okay, I want to end off this discussion of bonds with a very brief discussion of pH. The definition of pH is that it is the negative logarithm of the hydrogen ion concentration. That's why the negative logarithm means it's 1 over the logarithm. So the smaller the pH, the higher the hydrogen ion concentration. So very acidic solutions like your stomach acid in around 1 or 2 pH, that has the highest concentration of hydrogen atoms. Sorry, hydrogen atoms. So why do I bring up pH? Because pH is very, very important to the function of our bodies. In particular, it's very important to the function of enzymes. And the reason for that is because low pH is a high hydrogen ion concentration. And the function of enzymes, you'll see, is dependent on the ability of an enzyme to change its shape. And that ability can be affected by pH. Therefore, pH affects enzyme function. And a good example of this is the pH in your mouth. pH 7 is a very good environment for salivary amylase to work. It's an enzyme that's responsible for digesting starch. You can test the effects of salivary amylase by taking a little bit of bread, rolling it up into a ball and putting it in your mouth and sucking on it. When you suck on it, the bread will start to taste sweet, and that's the result of salivary amylase digesting the starch into individual glucose molecules. When you swallow that chewed up bit of bread into your stomach pH is in around 1, and that's a very good place for peptidase to work, an enzyme that's very good at digesting proteins, but that will inactivate salivary amylase, so the enzymes that you swallow from your mouth will become inactivated in your stomach. In the next lecture, we will start to look at complex biomolecules. You'll see that proteins make up the majority of complex biomolecules, followed by nucleic acids, carbohydrates, and lipids.